Well, good morning, everyone, from everyone who joins us in Japan, and good afternoon and good evening for everyone else who joins from other parts of the world. Thank you all for joining us to the Embodied Cognitive Science Seminar. Today, we are very happy to welcome Jun Tani. Jun Tani is a professor and the leader of the Cognitive Neurorobotics Research Unit here in OIST. He's also a visiting professor in the Technical University of Munich. He's an engineer and he has been researching cognitive neurobiotics and adaptive behavior for over 20 years now. His book, Exploring Robotic Minds, Actions, Symbols, and Consciousness as Self-Organizing Dynamic Phenomena, aims to answer the question of how do our minds work, and covers a wide range of topics and disciplines from deep neural networks and chaos theory to cognitive science, psychology, and phenomenology. Today, Professor Tani will be talking about extending the framework of predictive coding for studying cognitive neurobiotics, and specifically to investigate how cognitive agents can develop structural representation functions through iterative interaction with the world. Professor Tani, thank you for joining us today. The stage is yours.
Yeah, Tish, thank you very much. Very, very wonderful introduction. So even for my book. So yeah, this is actually a book. So if you're interested in, so please, look at. Okay, so my talk today is first I'm gonna review overview of predictive coding, active inference, and especially related to the model using recurrent neural network, which I have worked on like 30 years, not 20 years, 30 years. And introduction, and then I'm gonna introduce a recent model, something called PVRN, based on the free energy principle. Because I'm going to use this one to the most of my talk, robotics experiment one. And robotic experiment including, first I'm going to talk about the social imitative interaction and between a human and a robot or robot and robot. Then move to the online go direct planning in a fluctuative environment. And then I'm going to talk about, if I have time, and I talk about development of sensory attenuation. That is a well-known phenomena, right? Like people cannot tickle by themselves. So, and through learning and how this kind of things could be developed, not as innate, but it could be developed through the sensory motor experience as a possibility I'm going to discuss. Then followed by some discussion. So that is today's menu. Okay, so then predictive coding is active inference is so predictive coding is a theory for the perception. So from the day of Helmholtz and Raoul Barrett and Princeton and other people discussed these a long time. So that idea is kind of is a subject have the top-down prediction about the world, and try to minimizing the error between the top-down sensory prediction and its bottom-up outcome by inferencing the latent states, that's internal states of the system is optimized so as to minimizing the errors. Then perception achieved. So that's the one way of thinking. So that's predictive coding. And the other side we have is active inference for action generation. That is, again, this is also minimizing the prediction error, but by changing the sensory inputs, by adequately acting on the environment. So this is by changing the environment rather than changing the latent state of the system. So the changing environment by acting. So this is a theory for action generation. So, but they're still based on the error prediction minimization. So, and these two are not separated the process, right? As an action and perception make a loop to the environment. So that is the essence of the embodied cognition. So, and so my group have worked on a relatively long time and some model analogous to the predictive coding, the active inference. So I didn't know the term, right? Predictive coding, active inference a long time, but without using that term, so I'm my group have developed something analogous or similar concept by conducting robotic experiments. So, but I'm going to show a brief sketch of, I would say my understanding of the how predictive coding active inference is kind of coexist or interact each other. So Then and we have considered a long time kind of a hierarchically organized recurrent neural networks, and then multiple time scale property this one has. So higher level is slowly operated, and time constant is larger, and then lower level is fastly operated. So, and then we might have kind of branching from maybe this is associative area prefrontal. Then we have one way is predicting about the proprioception, own motion, proprioception. In case of the robot, it could be a joint angle, right? It's predicting at each time step. The other is kind of predicting about vision or exteroception. So we might have some kind of the intention. So then intent to act, but that is actually intent to predict what is the outcome of the vision, as well as how it goes in the motion, so movement, joint angle, so proprioception. So this is going to be proactively acting on the environment by making the action. So that is this one is a kind of predicting the next motion, movement, joint angles. And that one is fed into the maybe robot controller in case of the robot. And then motor torque generated, acting on the environment. Then we're going to have a state change, hidden, usually it's hidden, but hidden in the environment, but a state change. It's going to produce the new sensation about the proprioception and the vision. Then we have a kind of a prediction of this one, and we have the outcome. Then we're going to have a prediction error. Then the prediction error is going to be a bottom up through the layer, and try to minimizing this error or conflict. So we have about all the level, we have the conflict between the top down and the bottom up one, but we want to minimize this one by updating latent state of each level, so higher level to the lower level. So that is a way to predict coding. The active inference is kind of interconnected. So that is the idea that one side we have a predict coding for the changing the mind state, latent state, for minimizing conflict or error. The other side is that the world state is changed by active inference. And these go through the interaction bottom and top down. But actually that's a kind of a twist. That means that the interaction take place all the level, not only higher level or lower level, but it's all the level. So then through this interaction, so we look at what kind of phenomena appears, and then using this kind of model, what kind of cognitive or phenomenological phenomena can be explained. So that is a study. So okay. So then, however, our model, especially our model with this one, is based on a deterministic model. So deterministic recurrent neural net, deterministically predicting. Then we have the problem of that many people say that no probabilistic treatment. Then this world might be look like a more probabilistic, how we can do it. And then some people, like a deterministic people, say that, okay, so then the probabilistic phenomena can be well imitated by deterministic chaos. So that is one thing true. However, more probabilistic machine learning people say that no, in order to treat probabilistic phenomena, we better to use a formal probabilistic model like a hidden Markov model or whatever. So then there is kind of the gap between the two communities. So are there any way to bridge the gap between the two? Then after I learned about the Preston things like maybe 12 years ago or something. So then okay, I thought that free energy is a way to minimizing the gap between these deterministic camp and the probabilistic camp. So, and then especially I thought this Preston's free energy is going to use stochastic dynamics. That is continuous dynamical systems plus stochastic noise kind of things. So that in terms of Bayesian. So then I thought that this may solve the problem, or maybe we can ask about what is the origin of probability in a subjective experience. We always feel about how probabilistic it's going to be, right? We often feel, for example, today's rain, then probably tomorrow gonna be fine, shine, or something like that. So we have something like that. Or maybe gambler would say, because this is the coin face side counts. So then the next one should be the other. Deterministically believing that. So that is a gambler, I think. So but it's kind of a same from looking at from the outside. That is, people say this is probabilistic phenomena. However, depends on the situation, human feel maybe differently. So that's kind of things that I'm kind of interested in. Okay, so then we developed something called the PVRN, that is the predictive coding based variational recurrent neural network. So then I because we use this model a lot, so I'm going to explain a little bit about this one first. So the idea is that it's based on equation, but you don't need to understand this equation. But free energy is here. That is a summation of one side is the minimizing prediction error or maximizing accuracy. So that one. The other side is we have this is actually in a posterior, we call. Posterior is kind of bottom-up inference of the latent state. So that's bottom-up things. And this is a prior is top-down. So before an observation comes, we're going to predict. So then this gap is minimizing. KL divergence between these two are minimizing. So that is saying that we're going to minimize the prediction error and also the gap in the middle layer in the prior posterior. So that's have to minimize. Then we're going to put some kind of okay. So here we have a something balancing between weighting to this W, so that is a constant, and put on this one. So and later I'm going to talk about this one. Now I'm going to the architecture. So that is so this is time step goes like this one: step 1, step 2, step 3. Then we have this is a probabilistic latent variable assigned for each step, and then it's going to be like we are following idea of sequence Gaussian prior proposed by Chung. So that is kind of a prior for each time step. So we allocate a variable. So and then that one is represented by the Gaussian distribution, mean and standard deviation. So each time step is going to be different. So, and then we're going to have the posterior is coming back after the observation of sensation. I'm going to explain this one later. So then this is kind of latent variable layer, and that one is mapped to the deterministic neural unit. So and then this one is necessary in order to, usually this one is the dimension is small, but if the nonlinear characteristic are strong in the modeling target, we need a good number of the D. So then we're going to have some of them, like we have this one for each time step. Then finally, it's going to be mapped to the prediction for the sensation, like a proprioception, like a vision is a previous figure. So we're going to predicting this one, and then we're going to have the reality of the observation. So at each time step. So then if you have the error, error is bottom up, and the back propagates through time. So that is using backprop, schema. And then this one is going to be further backprop to the latent variable, the probabilistic one, and it's try to change the posterior in the direction of the minimizing this error, as well as because we have KL divergence between the posterior prior have to minimize. So therefore, this is going to be changed. So each iteration we will update for minimizing the accuracy and for the minimizing posterior prior KL divergence by updating this one. In the case of the learning, we're going to update the connectivity weight also. So, okay, so that is the main thing. So then then what we did is something like we changed the multiplier W by effect of the balance changes between this term and this one. What kind of a structure developed? So that is something related to the discussion about the deterministic probabilistic that I will show from the next slide. So one simple experiment. This is not embodied at all, but is to understand the characteristic of PVRN. This one is very illustrative. So the idea is that so we let the network of PVRN to learn about probabilistic events by using this kind of a probabilistic finite state machine. This one is after the 1, 0. Then after that is a 170% is 0 is 30%. And back to here and 1, 0. So we have a deterministic state transition here and here. However, here is going to be probabilistic. So then using this kind of a probabilistic finite state machine that lets the network train about it. So the target comes 1, 0, then 1 or 0. So this is a question. 1, 0, and the 1 or 0 comes. So we're going to train this kind of a probabilistic sequence by using this one, and then by changing the W. So W, then what will happen? So then we did this is a two case of comparison. Case of the W 0.1 is relatively large, and the W 0.0.25 is a small. So then we're going to train the network, and this is a result of the output. And this is saying 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1. So it's coming out, 1 is more, so probabilistic 70. So, but anyway, this is, looks like reconstructing this one in terms of output. And then when we look at the prior sigma, the prior sigma is almost 0. Okay? And then mu is almost 0. So that means that is this probabilistic latent variable is this one is almost, this one is deterministic. So because sigma is 0, so no noise source in the network. And if we put the W is a relative in a smaller, then situation changes. This output part is the same. So, but the prior part is, so whenever this question state of this one comes, so that one's gray, it's going to be goes up, right? But this one is small. So S1, S2 is small, but this one is going to be large. So that is sigma becomes large in the prior. That means that it's using stochasticity at the right timing, good timing of the state 3. So therefore, this one is probabilistic encoding. This one is deterministic encoding. Actually, this case is that we found that something called Lyapunov exponent that is showing positive. So that is actually means that chaotic dynamics is generated this one. So that is so point is that the same fluctuated probabilistic sequence comes, and then it depends on the observer. We're going to treat it as a deterministic but a chaotic dynamics with initial sensitive one, or look at it by the stochastic process. So that is two ways possible. Depends on the setting of the parameter of the system. So then point is that so by changing multiplier W, if we have fluctuated spatial temporal pattern, but if we set W is larger, it's going to be embedded in a deterministic chaos. But if you W set smaller, it's going to be embedded in a stochastic process. So that is we have. So that is the same model can explain so either deterministic modeling or stochastic one. So, but the characteristic is going to be different. So if we set the W is very larger, and then something called high precision prior, that the sigma is very small. So that's predicting, the system thinking that my prediction is very correct, precise. So, but on the other side, if it's run as a prior sigma large, means that the system is thinking that my prediction is probabilistic. So it's kind of even though the mean is the same, the mu is the same, but the sigma large is that. So I'm going to predict that the mean like this one, but I'm not so much sure exactly like that. So then this case is more strong top-down, and this case is a weak top-down belief. So, okay, so, and then this kind of network is going to be used in a multi-layer. And we developed something called multiple times recurrent neural network 15 years ago. So, but the same way, so it's kind of this part is slow with a large time constant, like this one. So this is activation dynamics. So tau is large, it's going to be slow, and the tau is small, it's going to be slow faster. So then this is a multiple level network is operated like a forward prediction, like go like this one from top down, and forward in time is predicting. And if you have the error we got from the observation, the error is bottom up and the back prop through time. So and then we're going to update in the posterior in all layers. So that is the way of understanding. So inference. So okay. So then the important thing is that so while, for example, we do the cognition in real time. So that is while we perceiving, and we're gonna simultaneously predicting. So that is we're gonna do like so it's kind of this is now, this is the future, this is the past. Whenever you got a new sensation, and then error is propagated, not only here, but there is a one step before, two steps before, kind of the window we're going to consider that all the error is back propagating, the updating the posterior again. So every sensory motor step, we're going to iterate a lot of iteration, like 100 times or something like that for the robot experiments. And then why are we going to do that? That is try to make the system well situated to the older experience, the past sequence. So past sequence should experiences that this one should be explained by its own. So that is reflecting the past. So by updating the posterior, once the current latent state, including both probabilistic one and deterministic, are situated to those sensory sequence came shaded to that one, then we can predict future. So the ones situated, then you can predict the future. So therefore, each sensory motor step, we're going to do the iteration of updating the posterior many times, like this one. So that is kind of we're going to use for the dynamic planning for the future. Later I'm going to explain. So okay, so then we're going to explain in describe the synchronized imitative interaction done by the Nadine and last year. So that is okay. So two robots. We have robot 1 and robot 2. So and then it's going to be intact. But the two robots, first two robots are pre-trained. So for generating, predicting sequence of the primitive pattern, which follow specific probabilistic finite state machine. So first, pre-train means that it's almost like we teach supervised manner. The robot standing in front of the mirror or something like that. And the robot is kind of his hand is grasped by the human experimenter. Actually, so this is kind of a teaching device for the robot. So human grasping this one, if the human move like this one, and the robot hand move like this one. So then the robot see that how own joint angle change, right? So while tutoring, and then because of the mirror image, he can see how his hand move in a visually. So then it's learns to generate movement, own movement pattern in terms of a joint angle proprioception as well as a visual coming input, so like a mirror image. So that is going to be learned. The another thing is that now the two robots is going to learn all movement pattern, but that one is almost same. So first movement A comes, and 80% for this robot is generating C. And then 20% is a B, right? However, in the case of a robot, after A, 20% for the C, 80% B. So therefore, in order to they synchronously imitate, generate the same pattern, and this state is going to be conflicted. So we intentionally including conflictive situation in order to look at how they arbitrate, how they tune by themselves, for in order to maintain the coherence between them. So okay, so and then the two progressive finite state machine taught to the robots are conflictive. And the training is rapid. Then we did this experiment by changing the W for each training. So small W, large W, something like that. So then look at after the learning, two robots interact by generating own intended movement pattern while perceiving the pattern generated by the other. So now two robots are kind of facing each other and looking at the other robots moving also. So then, but that is the robot is already trained to visually predict, but when the conflict comes, so then it has to be resolved. So then architecture is like this one. So like so robot one, robot two, we have the both are going to be predict with the prior, and then it's going to be the one is branching to the vision prediction. The other is a kind of proprioception joint angle, and that's fed into the controller, the actual movement of the robot one generated. And then that one, it can be observed by this robot. So it's going to be predicts the vision, and you got so. And okay, so this is a proprioception and the movement generated. And then if you got the error, so this guy is predicting this one, and the error comes, and the error is going to bottom up, changing the posterior update. So, and then simultaneously, so you got the error in here and updated the posterior. So then both sides are changing the posterior so as to maximize, minimizing free energy. So the specific question is that what sorts of interaction can emerge? And do they always imitate each other synchronously, or do they sometimes generate their own intended movements by ignoring the other? How does a W affect the ways of dynamic interaction? So let's look at robot experiments. Okay, so now what I'm going to show is that now this robot is trained with small W. This robot is trained with large W. Then after the training, they're going to interact. So this is a high W. So, and then he is now doing B pattern, and this robot is following. So this is now back to the A pattern and the synchronous. That's a shared part. So then, so here is current time, and this is predicting future. So this robot current time is here, and this is past window, past, and the predicting future. And then you see that this guy's prediction future is almost very stable. Like now he's doing the A and predicting about B and the A, B. So this guy's kind of prediction is very unstable. So now it's doing the C, but over he's kind of leading. So this guy is a little bit faster than right. So this guy is leading. So And then he's doing the pattern he doesn't want to do. So because he preferred C rather than B, but he generated B and he's going to be following it. So, okay, so the next is kind of both are strong. W is large, both are W large. Multiply W is large. So then both are very predicting stable, but they are after A pattern, they are kind of conflicting, but they are okay. So A is okay, but the conflicting state coming. And this is always generating B, this guy is generating C. So conflicting. In case of the both are set larger W. This case is that two robots set with smaller W. Very much fluctuating for prediction because sigma goes to be larger. So it's kind of sometimes we see turn taking like a behavior and the leader changes. So okay. Okay. So then what we see is something like in case of the red one, robot one set with small W, and the robot two with set larger W. And actually, maybe this is a little bit, you may not be see, but it's black one is posterior, and the green one is prior. The black one is posterior, and the green one is prior over lower level. So then we see that the kind of when set W is small for robot one, it's going to be a gap between. So that is, because W is kind of regulating that's tail divergence part, and W is small. So then it's going to be, it's not exactly equal. So prior posterior kind of a deviation is allowed. But in case of the W sets larger, it's going to be very, not so much, when sometimes here deviated, but mostly kind of the same. So also time constant effect, this is a lower, higher level of a latent variable. It's kind of slowly changing, but it's actually encoding of starting. So this is starting with A, So it's kind of synchronized with this one. So a little bit delay, but so that's kind of a representation comes out. Okay, so then the point is like, so when W is set very larger, and then prior going to be the very, prior sigma becomes very small. So that precision becomes higher. So that's why the posterior is going to be attracted by the prior. It goes to this side. So therefore, generation is very much based on the prior. Prior means that own intention is more enhanced rather than sensation. But on the other hand, if we put the prior in a set that W is very large, small, then prior dynamics has a larger sigma. So that is a less precise prediction. It's thinking itself, my prediction is not so strong. That's why posterior is attracted by the observation. So that's why this robot is following not on intention, but observation. So that's why this robot is going to be reader. This robot is already following observation from him. So that's kind of relation is developed. Okay, so then we do kind of a human robot interaction using the same model. So maybe like so this robot is already trained with a set of movement pattern, but he's kind of grasping his robot's hand, try to kind of degenerate already learned pattern. So using error regression and then so, but sometimes he's gonna follow his movement, but sometimes he's gonna do some against movement. But the important thing is that when the robot generates something against movement to him, then the human, he can feel intentional robot in their hand through the active inference. So that is kind of he can feel will or intention by the force of this robot when try to guide this robot. So, okay. And then, so now, yeah, move to the last topics. Is okay, so 5 minutes. So online go direct planning by extended active inference. So it's done by the Dr. Matsumoto. And so online planning for the future while reflecting past is the idea, something like, so again, this is now, this is a past one, and then you have the observation, and then got error, and then the best, and then posterior best situated. Then we can do the, so, and this part is reflecting the past, the minimizing evidence-free energy, like this one. Then once it gets situated, then you can maybe the outsider provide a goal. So this is the goal state. So like a visual state of the goal. So you have to achieve like this one. So then robot is going to think about it in an online manner. So this is the expected future visual perceptive sequence, and then try to match this one, minimizing the error between. However, if you cannot minimize and the error propagates, and then updating the posterior in the direction of minimizing this error, as well as minimizing the KL divergence between. So that is something called planning for the future by the minimizing expected free energy. So then actually the system is going to do is minimizing this future free energy as well as past, so evidence free energy simultaneously. So that is actually updating all posterior in each step in each layer. So as to generate the situated goal direct planning for the future. So then this is that when you while operating in online and then one step ahead, so then still the new sensation coming, you're going to be reflecting the past many epochs of and then also you replanning. So, but the usual case is just one step changes. The plan does not change so much because situation does not change. But sometimes new step comes and then suddenly some obstacle comes, something like that, and then it's going to react very much. So that is kind of risk of the generating high free energy. So therefore have to minimize, and both we're going to think about past and future. And the past and the future has to be connected in smoothly and rationally, but it has to be done in real time. So that's part of real time is also interesting part of the study, but we didn't do so much yet. So, but anyway, so, and so then we do this actually in multiple layers. Well, one thing I like to say is that this schema is a bit different from the traditional planning schema. That is because we do it, everything is planning is usually we do in a motor joint, motor space, a large space, right? But what we do is kind of the latent state. So progressive latent state, we're going to look at. This is usually low dimensional. And we search for the very small space. So that is something good. And then also, we do the planning for future while reflecting the past, as I explained. That is also another big important characteristic of this scheme. So, okay, so then we're going to show the first simple experiment. Like, so this robot is kind of looking at this object. So this is a goal. So it has to be achieved. Then now object located here. So now, what do you see here? This is a future planning, and this is a latent variable. So, and this is a past. Okay, so then now he got the plan, and then he's going to put it. So that's successfully. So that's no problem. Okay, so then. So this is another one. So this is a new goal, another goal. So then robot is going to start to generate. So you see that as time goes by, it's past is kind of fluctuating a little bit, and the future also. but it's not so big noisy event. So then it goes relatively smoothly. So, and then next one is in a kind of dynamic replanning after humans interference. So it's like now the robot is going to move the object to here. So goal was not shown, but he is going to do it. Then while he's doing, so it's kind of a, interference making. So therefore, now robot is going to be problem. So have a problem. And then you see that the past is going to be changed gradually. And then try to make a future plan. So now almost future plan generated. So, and then he's going to do it, execute it. Yeah, he actually can do it. So, okay. So that is the point is here. So when first time robot grasping an object and try to put on there, but the human interfere. So then the scale divergence between the approximate posterior and the prior becomes larger due to the interference. So unexpected things come. So then, and what we observed is that when the robot was interfered, as I wrote, the scale divergence increased both for the past and the future. So then the replanning for the future was performed, while optimal latent state for the past to connect to the future adequately was inferred by minimizing the both evidence-free energy and the expected one. So then robot is sometimes successful for this unexpected event, but is currently what we are very much working on is that because the robot often fails after interference because never experienced something like that. In such case, experimenter assists the robot physically. So while robot failed, then grasping his hand and then helping him to achieving the goal. So then such episodes are retrained, aiming for better performance. It's failed, and then assisting him, and then robot learn about such failure case of how it can be resolved. So, but the not important thing is that the experimenter can feel the intention of robot through the physical tutoring. So, because he is grasping his robot's hand, he can feel which way he wants to go. So his intention can be understood. In that, under such a condition, trajectory for tutoring is generated, co-developed by the robot and the human, and then tutoring goes. So that is kind of co-developmental learning. So idea is something like exploring novel latent space. So we have first, we first in our initial training, habituated region generated in a latent space in the prior dynamics. Then novel experience comes like this one, going outside the habituated region. So that one is maybe human counterpart, explore the conflicting movement trajectory as novel region. So that is kind of intentionally suggesting robot to go this way, which robot never experienced, but by feeding robot against force. He wants to go to this way, but experimenter is suggesting this way. So then feeding kind of against force. That is scale divergence, right? So then, or maybe, so we're gonna set W or here smaller. That means that it's kind of a posterior prior is allowed to be increased. So that is kind of a robot can generate around things. So because going out is more allowed because W is smaller. So in that way, the new experience can be made. So it's kind of, it's something like similar to the idea of intrinsic novelty rewarding or intrinsic motivation. So, and the habituated region can be gradually increased by incremental learning of such novel experience. But that is we are now working, and then not yet completed. So in the future, I can report the results more precisely. So I don't go this one because it's now finishing. So just to go to the end. So much. So then discussion is that why I consider variation recurrent network is good for modeling embodied cognition. One is that first is that it's based on the continuous recurrent network. That is a seamless interaction between the top-down subjective mind, the bottom-up sensory reality in analog metric space. So that is very important. In the old model, is the conventional one is that the higher level is more graphical model or symbolical model, but the symbolical space and analog sensory space, and they cannot interact directly because they don't share the metric space. But in using recurrent network, it's kind of a higher level, also analog space, and then the bottom-up sensory things, analog space, and then they can interact very densely at the least. Right? So that is seamless interaction is possible. So that is we have a subjective mind, now analog prediction, and we have bottom-up one, and we can interact, and both sides are going to be changed through the seamless interaction. That is one thing. But now we have a kind of variational-based account. So the accounts for the development of elastic dynamics. I would say deterministic dynamics is not always elastic because you set the initial state, it doesn't change. So future is determining like a steel. But variational recurrent network is because we have a prior very precise one is going to be more steel-like. But if the precision is lower, then it's going to be more elastic, allowing a change in the future. So that is we have a strong top-down, bottom-up, and push and pull relation. It depends on how much you strongly believe in, right? And sometimes it's going to be believing is very weak. So then bottom-up is push up more. So that kind of push and pull is going to be more physically embedded. So, and that kind of thing is possible using this kind of model. And finally, I didn't discuss anything but about the consciousness, but phenomenological consciousness things, very much we can discuss. Then the long time I'm talking that the non-conflictive situation with free energy minimized, that's smoothly everything. So that is that everything goes very smoothly and go along the trajectory habituated, then that's going to be automatic. Therefore, that's going to be the less consciousness. On the other hand, in conflictive situation, F should be minimized. Free energy have to be minimized with effort. A lot of the search, that's going to be the more deliberative, and then it requires more efforts and the resource, and then it's going to be more conscious. Okay, so that is end of my talk today. So yeah, I used up a little more time. So thank you.